Alright, oops, dropped my pencil. Right, I'm back. Prop 26 says, if two triangles have the two angles equal to two angles respectively, and one side equal to one side, namely, either the side adjoining the equal angles or that subtending one of the equal angles, they will also have the remaining sides equal to the remaining sides and the remaining angle equal to the remaining angle. So this is a long proposition, and it's a little bit tough to parse, but it's actually, we're proving two different congruence theorems in this one proposition. So not only is the proposition itself long, the proof also is going to be probably the longest proof that we've seen at this point. So first of all, what is this proposition saying? So, all right, let's go through it sort of line by line. If two triangles have two angles equal to two angles respectively. Okay, so that part of the proposition is just sort of fixed. It's saying, assume that we've got triangles ABC and angle ABC right here, sorry, triangle ABC and DEF, and angle ABC is equal to angle DEF, angle BCA is equal to angle EFD. So the angles at the base of the triangles, the way that I've sort of drawn them, the angles at the bases are the same. And then on top of that, we're going to assume two different possibilities. One, we're going to assume that either the side between those equal angles are the same. So the first case is we'll assume that BC equals EF, and the conclusion that if BC equals EF along with these angles being equal, then the triangles themselves are congruent. So that's the first theorem that we're going to prove. The second one that we're going to prove is if the side subtending one of the equal angles is equal. So kind of you can take your choice, either assume that AB is equal to DE or that AC is equal to DF. It's the same thing either way. So what we're looking at is basically angle side angle and angle side. So the first, and that's why this is like a long proof, because we're technically proving two different theorems. The reason that I think Euclid put these both into the same proposition, my guess, is because the method of proving them is really similar, but it's not actually the same. They use different propositions in each of them, but the proof method is similar. It's kind of a similar tactic. Okay, so the first case is that we're going to assume BC is equal to EF, which means that we have angle side angle similarities or congruence. So this will be, yeah, angle side angle. And then the second one, again, you can take your choice. You can either set AB equal to DE or AC equal to DF. It's the same thing. I'll choose AB equal to DE. Which means then that we would be looking at angle side congruence, as we call them today. So we'll start off and we'll do both of them. So I'll start off with this very first one. Looks like the angle's a little bit funny. 1 second. There we go. Maybe that's a little bit better. I don't know. All right. So first, we'll assume that BC equals EF. And I think that what I want to do too up here is just kind of like make just a quick sort of note to myself that all of these together with case one, where we have angle side angle, what else do we need to prove here? Because we're proving that the triangles are going to be congruent. Well, the first thing that I'll need to prove is what we're assuming in part 2. So first, if BC equals EF, then I'm going to prove that AB equals DE. I'll also need to prove that AC equals DF, and that the remaining angle, CAB, equals angle FDE. Running out of room there. So just kind of like setting out, because yeah, there's sort of a lot of moving parts in this proposition, so we want to stay really clear on what it is that we're trying to prove. Okay, so if we're assuming that BC is equal to EF, here's everything that we need to prove. How are we going to do it? Well, one of my favorite methods of proof, the most controversial one, is contradiction. So I'll say toward a contradiction, assume, in particular, we will assume that this fails, that AB does not equal DE. Well, if that's the case, then we can assume without loss of generality one of them is bigger, so we'll assume that AB is larger. Right? Like if they're not equal, then definitely one of them is larger than the other one. So we'll say, all right, then it's AB that's larger. All right. So what do we do next? We place on AB point, what do we call it? I think we call it G. Yeah. Place on AB point G such that BG equals DE. And this would be proposition, oh, I don't need this. This would be proposition 3 if we wanted to. So we're assuming, yeah, so AB, G, we'll say, I don't know, maybe G is like right here, because they are the same, so you just have to kind of go with the flow, suspend some disbelief. Okay. So G, yep. And then we'll also join CG. Okay. And do I want to do a dotted line or a solid line? I'll do a solid line. Just make it a little bit more faint, maybe. It's not going to come out more faint. That's fine. Okay. So we're just assuming that that BG right here is equal to DE. Well, what do we get from that? If we assume that, what do we get? I'm having some camera troubles. It looks like it's not as focused. There, that's a little bit better. All right. Well, if that's the case, then let's list out everything that we have. Well, we have that BC is equal to EF. We just, by construction, we have that BG is equal to DE. And we've already been given that angle ABC, which is the same as angle GBC, is equal to angle DEF. Well, that's side angle side. So yeah, so I'll just say the triangles are the same. Oops, not ABC, GBC. GBC equals triangle DEF. Yeah, and this is from Prop 4. Side angle side. All right. Well, if that's the case, then in particular, angle GCB is equal to angle DFE. GCB is equal to angle DFE. But we also know that angle DFE, which is the same as EFD, is equal to angle BCA. So in other words, it's equal to angle ACB. Well, why is that a problem? But, and here's what I would say, Euclid doesn't say this bit, but notice that ACB is equal to angle ACG plus angle GCB, which is a contradiction, because clearly then ACB is larger than GCB. But then just right here we're saying they're the same. So it's a contradiction. So it must be the case then, I'm running out of room, so I'm just kind of like going to shorthand this last little line here. So it must be the case that AB equals DE. And if AB equals DE, so I don't think that I'm going to have enough. I'm just trying to keep this part of the proof on the same paper. But notice that if AB equals DE, we know we're given that BC equals EF, and that angle ABC is equal to angle DEF, because that's given to us. So by side angle side, these triangles are the same. I'll say thus, triangle ABC equals triangle DEF. By prop 4. Okay, so that's only half of what we set out to prove, though. So we've just proven the angle side angle situation. Next, we're going to prove the angle side situation. And again, just to kind of like know where I'm going, in this situation, when we assume that AB is equal to DE, again, we're assuming that, or the conclusion is going to be that these triangles are congruent. So part of what we have to prove then is what we sort of just assumed. So if we assume that AB equals DE, then one of the conclusions is that BC equals EF. And then these two pieces will still hold, like, because the triangles will be congruent. So in addition to BC equaling EF, AC equals DF, and then angle A is equal to angle D. So that kind of stays the same. So this will be the big, and it'll be the same thing in that, like, once we prove that BC equals EF, prop 4 gives us the rest of this. All right, so how do I want to do this, though? Because I need a new page. I would like to, as much as possible, keep the diagram on the page here. Let's see. Just do this to try to prevent so much smudging, but we'll see if it works this time. All right. So I'll say, boom, that part's done. Okay. Now assume AB equals DE. And by the way, if you want the practice, if you're kind of interested in it, this would be a really great place to try to practice this proof on your own. So yeah, assume that AB equals DE, see if you can prove the rest of this. It's going to be very similar. It's going to be a contradiction argument, at least the way that Euclid does it. It's a contradiction argument. It's not completely symmetric, though. You do end up using a different proposition. It's a little bit trickier than the one that we just did, but it's a really good practice, too, if you are trying to get some practice with writing proofs. All right. So assume AB equals DE, and again, toward a contradiction, we'll suppose that BC is not equal to EF. And again, well, if BC is not equal to EF, one of them is longer. So suppose that BC left and more, assume BC is longer. Alright, so similar setup. Let's say we'll place H on BC such that BH, right? Yeah, BH equals EF. and then we'll join AH. So on BC, we'll assume maybe right here is H. Oh, yikes, it's ugly. Okay, so there's our AH. Well, then what? We're going to get something very similar. Then, well, I'll just rewrite this. BH equals EF. So BH equals EF. We already know that AB is equal to DE. We're given that. And the angle between them, ABC, is equal to angle DEF. So, angle BHA equals angle EFD. And really the triangles are ABH by this assumption. Triangle ABH is congruent to angle DEF, but the important part is that angle BHA, just to cut right to the chase, angle BHA would be equal to angle EFD. And that should be prop 4. Yep. But here is kind of where things get a little bit different from the last proof. We have to use a different proposition than the one that carried us home in the last piece of this proof. So, in particular, what we use is the fact that angle BHA is an exterior angle to triangle AHC. But angle, so here's what I'll say, angle BHA is an exterior angle to triangle AHC. And by prop 16, an exterior angle must be greater than either of the interior and opposite angles. Okay, why is that relevant? Let's take a look. So angle BHA is right here. We said just a moment ago that that is exactly equal to angle EFD. But what do we know about angle EFD? Well, angle EFD is equal to angle BCA. This is a contradiction then. That's the contradiction. So this is a contradiction. Since angle BCA, equals angle EFD, which means that angle BCA also equals angle BHA. Alright, this sentence is a little bit clunky. It's become a little bit clunkier than I intended it to be. Okay, just make sure I'm keeping everything straight. So yeah, BCA equals EFD and EFD equals BHA. So, right, angle BHA, which is equal to EFD, is also equal to BCA. But angle BHA must be greater than angle BCA. Right? Yep. And that's the contradiction right there, is that we just found that this BHA, which is exterior to AHC, is equal to the interior and opposite angle, which is in violation of Prop 16. So, our original assumption was wrong. BC equals EF. And then now we're pretty much done, because if BC equals EF, AB equals DE, and then the angle between them is the same. So, just to not get so wordy by Prop 4, triangle ABC equals triangle DEF, which gives us the last of what we needed. So, there it is. That is a long proof. But we did it, and it's very clever. QED, therefore, etc.